Okay, thank you very much. Yeah, I'm Mariana. I'm based in Politecnico di Milano, same as Kutai. And I'm working with Professor Croce and Dr. Stefano Cacciola. Okay, so my work has something to do with what Thomas just spoke about. So how do we know the performance of a floating turbine in these like movement conditions? And Thomas spoke about how you can see the wake behavior using the wind tunnel measurements. And let's put a pin on it because I'm going to show you a little bit later just a tiny bit of the work that I have done with Thomas. But also we can, when possible, measure power thrust. And we can do this with engineering models. So the two engineering models that I'm using are unsteady blade element momentum theory and lifting line free vortex wake method. So these are two, let's say, like mid-range fidelity models. Like simplest is the unsteady blade element momentum theory. So it's just a one-dimensional actuator disk blade element, varying with time, and we use all of these correction factors to help get the results that we that are more faithful to the reality. And the other one is the lifting line free vortex wake method. So we represent the rotor here with a lifting line. We consider the velocities created by the trailing vortices shed from the blade, and we calculate the circulation relative to the inflow velocity using CP and CT curves. So let's look at MOITO again. Same characteristics that Thomas already said. And how do the engineering models go against the MOITO characterization? First, let's look at the power coefficient. So we have in the dashed black line the experimental data from MOITO, and blue line is the unsteady BEM, and the green line is the free vortex wake. And we can see that, well, we are not really matching, but the error between them is quite small. So for the BEM method is about 5%, and free vortex wake is about 7%. And it just has more to do about how the let's say like maximum CP is sort of traveling from what we read in the experiment. We see the same case with thrust. So here we have the same, but this is thrust coefficient. And the error is a little bit lower. So these models are used then going forward. We accept these errors as being low enough to continue. And we use the same type of prescribed motions as Thomas already spoke about. It's harmonic motion with an amplitude. I'm going to use here one that is 5% of the diameter, and a reduced frequency from 0 to 1. So it's quite a small range of reduced frequencies. And I'm going to show also the two motions that Thomas already spoke about for brevity's sake. So here we can see BEM in blue dots and free vortex wake in the green stars. Unfortunately, there are no experimental data. It's just because the frequency of the motions is not readable by the instruments that were available at the moment. But we can see the same sort of behavior in power and thrust fluctuation. And by fluctuation, I just mean like how much it deviates from the mean of a static case in different frequencies. So one amplitude in different frequencies. So it's kind of linear, but we see that the free vortex wake is growing at a slower rate than the BEM model. Also quite small errors between them, 4% for power and 1% for thrust. And okay, MOITO small, what if we look at big turbines? Do we see the same kind of behavior? So I've chosen for now 2 turbines. So it's the NREL 5 megawatt and the DTU 10 megawatt. And we see a linearized fluctuation in surge motion. And by that, I just mean that the fluctuation is linearized by the reduced amplitude so that we can compare different amplitudes in the future. I'm not going to show this right now. And here we have the reduced frequency so that it's also linearized. And these 2 lines we see are MOITO, which is linear but quite high, different in reference to the other 2. If we zoom in to the 5 megawatt and 10 megawatt, we see that it's also a growing tendency, but again, at a much smaller rate, and also a much smaller fluctuation. And in general, we see that the BEM is always shows a little lower fluctuation than the free vortex wake. We see the same situation with thrust. Again, yeah, same kind of behavior. If we look at sway, MOITO shows a kind of growing curve. However, I don't even need to zoom into the other big turbines because they actually show no difference in fluctuation when the frequency increases. And in thrust, we see there's a higher thrust fluctuation for the bigger turbines, but again, it's not dependent on the frequency of the motion, which is different from what we see with MOITO. So, okay, if you remember the pin, I'm going to quickly throw a parenthesis here. So Tomás was speaking about the potential of free vortex wake methods for analyzing the wake. And here I'm showing in the dotted lines the results that we got in Milan from the wake. So from 2D down to 10 diameters downstream in the sway case. And what we saw is that very close downstream, we do have a good correlation between experimental and model data. However, right after 4D down, you lose this exactitude, and basically in the far wake, we cannot really compare because the error is already too much. So let's go back. Now we've seen 3 cases of horizontal axis turbines for 2 motions, and now I want to know, do vertical axis wind turbines show the same behavior? And for this case, I've chosen 2 VOTs so far. So the first one is a 10 kilowatt wind turbine, which well, the blades were developed in where I did my secondment in CartFlow, so I have the data for that. And the other one is the CTRL 1 megawatt model. So what happens? Again, I put the NREL 5 megawatt and the DTU 10 megawatt, but now we've added this ST is the CTRL, and then this is the 10 kilowatt. And we see that the behavior is quite different, and there's not really a relation between the both vertical axis turbines. However, I can say that in the C12, actually the biggest or the fastest frequency affected the power the least. And we see the same motion, the same in thrust. It's very small. And then for the 10 megawatt, there's no change at all. And this last point at very high frequency seems to be a sort of outlier. I'm trying to understand this. Okay, and for sway, if you see the numbers here, it's like 0.1%. So the fluctuation is not really there for the vertical axis turbines. So for thrust, it's also almost non-existent. So to conclude, the power and thrust fluctuation of the wind turbines of different sizes and types were obtained for prescribed harmonic motions of 1 degree of freedom with a reduced frequency of up to 1. So a range between 0 and 1, and a motion amplitude corresponding to 5% of diameter. And we saw that the fluctuations experience a linear growth proportional to the frequency of motion for the horizontal axis turbines, but we didn't find behavior that we can sort of linearize with the vertical axis. We have bigger errors the smaller the turbine. And yeah, the vertical axis turbines don't really experience a lot of variations due to the motions, which is or could be one of the many aspects to think about when we want to try to like give some credit to vertical axis turbines. So there's still a lot of work to do. I would like to include CFD simulations to validate the modeling, to study a wider range of frequency and amplitudes. Here I only showed you one amplitude, but there are, I already have some more. Also to study the results of all the degrees of freedom plus complex motions due to different types of platforms. So that could be something interesting to show. And the analysis that I did, the two vertical axis wind turbines were both like H-type Darius, but I know that the bigger designs now are more of this omega shape. So it's another thing to consider. All in all, the work is still ongoing, so yeah, it's on its way. So with this, I finish, and I'm open to questions.
Okay. Thank you, Mariana, for your presentation. So are there any questions? Yes.
Thank you, Mariana, for the presentation. Just before my question, maybe you explained it, but I don't remember. Yeah. Can you say again which floater did you use for your simulations?
There is no floater, it's just a prescribed harmonic motion.
Okay, and so you say in your outlooks, you will study more complex motion. It's like time series of
yeah.
motions.
So actually, Xiaoming has provided me with some time series that I want to include. It's just, of course, this kind of time series just takes a lot of computational time.
For sure. Okay. Thanks.
Any other questions? Yes, Thomas.
Yeah, thanks for your talk. It's very nice to see that the wake matches well in the near wake when you show the comparison between experiments between a free vortex code. I was wondering about the far wake. Like, it really looks like it's completely unsymmetric. Do you have an idea why it's that? Is it like the time of simulation that is long enough to reach this convergence, or it's just that after when we are in the far wake, the model really perform bad in a sense, or do you have an explanation for that?
The error just kind of piles up the farther away we go, because it's just panels, so the panel moves, and so that's why it shows this like non-symmetrical form. Okay. Also, the model does not take into consideration the nacelle. Like Mojito has a very nice big nacelle, and the model does not.
So there is one question online. It is about the wind speed that you have used for your simulation.
So I have used the rated wind speed for each turbine.
Okay. Other questions? So I might have a question. It was not clear to me why you had such high power fluctuations for the Mojito case and not for the large wind turbines. Do you have an explanation for that? That you have so much difference in terms of, I think it was normalized power fluctuation or something.
Yeah, normalized power fluctuation. I think just the reason for that is that Mojito is so small, right? Mm-hmm. And the motions are actually, I don't know, it's a lot
so maybe I can ask the question differently, but did you have kind of controller in your system?
No,
there is no controller, so that cannot be explained by different controllers or things like that, so you would have a damping or...
Yeah, no, I think Mojito is just, it's sensitive in the sense that it's so small that each change just represents a percentage, a big percentage.
Okay. Any other questions in the room or online? Okay, so let's thank again the two speakers from this session.